Hello there, and welcome to the Sleepless Scientist, a quiet place in the cosmos where your thoughts can unwind and knowledge becomes a soft lullaby for the night. Tonight's journey will take us into a question that humans have carried for thousands of years, often without even realizing it. A question that begins with something as simple as looking up at the night sky and wondering just how far it all goes. But before you settle in and get cozy, I'd love if you could take a moment to like this video and subscribe, only if you truly find these quiet explorations enjoyable. And when you're ready, leave a comment to let me know where in the world you're listening from and what time it is for you right now. It's always such a quiet kind of wonder to imagine all of us, scattered across the planet, each in our own small pocket of night, sharing this same sky in different moments. Now, feel free to dim the lights, maybe turn on a fan for a soft, steady hum, and let your body settle into whatever position feels most comfortable. There's nowhere to rush to, no need to hold on too tightly to each idea. If your mind drifts, that's perfectly fine. Let it wander. We'll still be here, gently unfolding the story. Tonight, we're going to explore how humanity measured something that, at first glance, seems impossible to measure at all. The size of the universe, its shape, its beginning, and perhaps, in a quiet way, our place within it. It's a story that doesn't begin with powerful telescopes or complex equations, but with something much simpler, a pair of human eyes gazing upward into the dark. And if you let yourself imagine it now, just for a moment, you might feel what they felt. A sky filled with countless points of light, still, silent, seemingly unchanging. A vastness that feels both close and impossibly far away. And from that quiet beginning, everything else slowly unfolds. If you were to take a single grain of sand and hold it gently between your fingers, it wouldn't seem like much at all. Just a tiny speck, easy to overlook, easy to lose. Now imagine for a moment that this grain of sand represents our sun, not the entire solar system, not the Earth, just the sun itself. And then imagine placing that grain of sand onto a vast beach, stretching far beyond what your eyes can see. A beach made not of ordinary sand, but of stars, hundreds of billions of them, scattered across a wide, slow spiral. This beach would be what we call the Milky Way galaxy, the enormous home of our sun and all the planets that circle it. And yet, even that beach is not the whole story, because beyond it, in every direction, there are more beaches. Not just a few, but billions of them, each one a galaxy, each one filled with its own countless grains of starlight, quietly drifting through space, separated by distances so large that even light, the fastest thing we know, takes millions or billions of years to travel between them. It's a scale that almost resists being understood, and yet somehow, from a small planet orbiting one ordinary star, humanity has managed to piece together this vast picture, to look outward from a single grain and begin to understand all the beaches. There is something deeply gentle and perhaps a little humbling in that realization, because we did not step outside the universe to measure it. We did not rise above it to see its full shape. We remained exactly where we are, on a small world circling a small star in a quiet corner of one galaxy among billions, and from there, we learned to see. If you imagine yourself lying under a clear night sky, far away from city lights, you might begin to sense how this journey started. The stars above you do not appear as distant galaxies or swirling structures. They appear as simple points of light, calm, fixed, almost like tiny holes in a dark fabric. For most of human history, that was all they were. There was no sense of depth, no sense of distance, just a dome of lights overhead, turning slowly as the night passed, predictable, reliable, comforting in its consistency. It made a certain kind of sense then to imagine that these stars were arranged on a vast shell surrounding the Earth, a kind of celestial ceiling holding the universe in place. Beyond it, perhaps nothing at all, or perhaps something unknowable. It was a simple picture, and for a long time it was enough. But even within that simplicity there was a quiet tension, because the human mind is rarely satisfied with stillness. It notices patterns, it asks questions, it wonders what lies just beyond the edge of what can be seen. And sometimes those questions begin very softly. A star that seems slightly brighter than the others, a pattern that shifts ever so slowly over time, a feeling perhaps that the sky is not quite as fixed as it appears, and then, once in a while, something happens that makes the question impossible to ignore. A new light appears where there was none before, a change that does not fit the old story, a moment that gently suggests that the universe might be larger, stranger, and far more dynamic than anyone had imagined. But before those moments arrived, before telescopes and measurements and distant galaxies, there was only this, a human being lying beneath a night sky, looking up and wondering. How far does this go? Is there an edge? Or does it continue, quietly, forever? And perhaps, as you listen now, you can feel a faint echo of that same question drifting through your own thoughts. Not urgent, not demanding an answer, just present, like a distant star itself. Because the story of how we measured the universe is not just a story of instruments or discoveries. It is, at its heart, a story of curiosity, a slow, patient unfolding of understanding. And like many things in the universe, it begins not with certainty, but with a quiet sense of wonder. If you return, just for a moment, to that quiet image of yourself lying beneath a clear night sky, there is something almost comforting in how still everything appears. The stars do not rush past you. They do not flicker wildly or rearrange themselves from one moment to the next. Instead, they move slowly, almost imperceptibly, tracing gentle arcs across the darkness as the Earth turns beneath them. Night after night, year after year, those same patterns return. The same constellations, the same familiar shapes. It is easy to see why, for most of human history, the sky was not thought of as a deep and distant place, but as something closer, something enclosing, a vast invisible surface stretched out above the world like a great dome. In this picture, the Earth rested at the centre, solid and unmoving, while the stars were fixed in place upon this enormous celestial shell. They were not scattered through space at different distances, but instead arranged neatly on a single, distant surface, all at roughly the same depth from the observer below. If you imagine it now, it feels almost like being inside a quiet, enormous sphere. The stars are like tiny lights embedded in its inner surface. Wherever you look, you're simply seeing a different part of that same enclosing structure. There is no sense in this view of stars being closer or farther away, no sense of vast empty regions between them, just a smooth, continuous canopy of light. And in many ways, this idea worked remarkably well. Because from the perspective of the naked eye, the sky really does behave as though it were a single surface. When the stars rise in the east and set in the west, they seem to move together, as if attached to the same rotating sphere. When constellations hold their shapes over centuries, it suggests that the stars within them are fixed relative to one another, like points on a rigid structure. Even the slow drift of the seasons, bringing different constellations into view, could be explained by imagining that this great sphere itself was turning, carrying the stars along with it in a slow, steady rhythm. There is a quiet elegance in this model, It does not require enormous distances or complex geometry. It does not ask you to imagine depths beyond comprehension. It simply wraps the universe around you, enclosing everything within a structure that feels complete, bounded, and understandable, and perhaps most importantly, it places you at the centre, not just physically, but conceptually. Everything you see in the sky seems to revolve around your position. The sun rises and sets, the stars wheel overhead, the heavens themselves appear to move in response to your vantage point on Earth. It is a deeply human perspective, and for a long time, it was enough. But even within this calm and orderly picture, there were small hints that something more might be hidden beneath the surface. If you watch the sky carefully, over many nights and many years, you might notice that not all objects behaved in quite the same way. Most stars held their positions relative to each other, but a few wandered slowly across the sky, tracing unusual paths against the fixed background. These wandering lights, what we now call planets, did not fit neatly onto the idea of a perfect, unchanging sphere. Their motion was more complex, sometimes even looping backward for a time before continuing forward again. To account for this, ancient astronomers developed increasingly intricate models. They imagined smaller circles within larger ones, layered motions that combined to produce the strange paths of these wandering stars. It was like building a delicate clockwork system in the sky, each piece carefully tuned to preserve the overall idea of a perfect celestial order. And yet, the more adjustments were added, the more the simplicity of the original picture began to fade. It still worked, in a sense. It could still predict where objects would appear in the sky, but it was becoming complicated, and complexity in science often carries a quiet message. A suggestion that perhaps the underlying idea is not quite right. Still, for all its growing intricacy, the notion of a celestial sphere remained deeply persuasive, because it matched what people saw, it matched their experience, and perhaps most importantly, it matched their intuition. After all, when you look up at the night sky, it does not feel like you're staring into an endless depth. It feels like something closer, something almost touchable, a surface of light stretched across the darkness. It is only with careful measurement, with patient observation, and eventually with new tools and new ways of thinking that this illusion begins to gently unravel. But at this stage in our story, that unravelling has not yet fully begun. The universe still feels contained, still feels centred, still feels in a quiet and reassuring way complete. And yet, just beneath that calm surface, questions are beginning to gather. Small ones, at first, almost easy to ignore. Why do some stars wander? Why does the sky change in subtle ways over long periods of time? And perhaps most quietly of all, is this dome truly the boundary of everything? Or is it only the first layer of something far larger? For now, those questions linger without clear answers. They drift through the minds of careful observers like faint currents beneath a still ocean. And as time passes, as more eyes turn upward and more minds begin to wonder, those gentle questions will slowly grow. Until one day something appears in the sky that cannot be explained by any sphere, no matter how carefully constructed. A new light, a change where there should be none, and with it, the first real crack in the idea of a perfect and unchanging heaven. There are moments in the history of science that do not begin with careful planning or deliberate experimentation, but with something far more sudden, something unexpected, a quiet disruption, a small break in the pattern. And for those who are watching closely, these moments carry a particular kind of weight, because they do not just add to our understanding, they challenge it. Imagine once again that you're living in a time when the night sky feels steady and complete. The stars above you have always been there. They follow their slow, predictable paths. They rise, they set, they return. Night after night, they reinforce the same quiet message. The heavens do not change. Now imagine that one evening you step outside, look up, and notice something that was not there before. A new point of light. At first, perhaps you might doubt yourself. Maybe you simply had not noticed it before. The sky is vast after all, easy to overlook small details. But then the nights pass, and the light remains. Not faint, not subtle, but bright. Brighter than most of the stars around it. Bright enough that others begin to notice too. Conversations spread, observations are shared, people compare what they see, and slowly a realization begins to settle in. This is not something that has always been there. This is something new. In the year 1572, such a moment unfolded in the skies above Earth. A brilliant new light appeared in the constellation Cassiopeia, shining so brightly that it could be seen even during the day. To those who witnessed it, it must have felt deeply unsettling. Because if the heavens were perfect and unchanging, how could something new simply appear? For many, the first instinct was not scientific but symbolic. A sign, a message, something meaningful, perhaps even divine. After all, in a universe where a change was not expected, any change at all could feel significant. But there were also those who approached the phenomenon differently. They watched, they measured, they asked a quieter kind of question. Not what it meant, but what it was. Among them was a careful observer who studied the position of this new light night after night. He noticed something subtle but important. Unlike objects closer to Earth, this light did not shift its position against the background of stars as the Earth moved along its path around the Sun. It remained fixed. And this detail carried enormous weight, because if the object had been close, its position would appear to shift slightly when viewed from different points along Earth's orbit. This effect is gentle, almost like holding out your hand and watching how your finger seems to move against a distant wall as you change your point of view. But this new light showed no such movement. It stayed still, and from this stillness came a remarkable conclusion. Whatever this object was, it was not nearby. It was far beyond the moon, far beyond the planets. It belonged to the realm of the stars themselves. Today, we understand this event as a supernova, the explosive end of a star's life, a sudden release of energy so immense that for a brief time, a single star can outshine entire regions of the sky. But in the 16th century, that understanding did not yet exist. All that was clear was this: the heavens had changed, and once that idea takes hold, even gently, it is difficult to return to the comfort of the old picture. Because if a new star can appear, then the sky is not fixed. If the sky is not fixed, then the celestial sphere is not perfect. And if it is not perfect, then perhaps it is not a solid shell at all. The shift is subtle at first. It does not immediately dismantle the old model. People do not abandon their beliefs overnight. Instead, the idea begins to loosen, just slightly. A quiet doubt settles in, and with that doubt comes curiosity. Could it be that the stars are not attached to a single surface? Could it be that they exist at different distances? Could it be that what looks like a smooth dome is actually something far deeper, something layered, something vast? At this point in the story, there are no clear answers yet, only the first real cracks in a long-standing idea. And what makes this moment so powerful is not just the event itself, but what it reveals about the nature of discovery. Because science does not always advance through grand, sweeping revelations. Sometimes it begins with something small, a point of light that should not be there, a detail that does not fit, a quiet observation that refuses to align with expectation. And from that small beginning, a much larger transformation slowly unfolds. As the new star of 1572 faded over the following months, it left behind more than just memory. It left behind a question that would echo through the minds of those who had seen it. If the sky can change, what else might we be wrong about? And as that question lingers, gently but persistently, it begins to guide the next steps in our journey. Because once you allow for the possibility that the universe is not fixed, it becomes natural to ask what its true structure might be. Not a shell, but something else, something deeper, something without a clear edge. And in the years that follow, one particular idea will begin to take shape, an idea that stretches the stars outward, beyond any boundary, into a space that may not end at all. There is something quietly unsettling about the idea of infinity, not in a dramatic or overwhelming way, but in a softer, more lingering sense, a feeling that something has slipped beyond the edges of what the mind can comfortably hold. For most of human history, the universe, no matter how vast it seemed, still had a kind of boundary. The stars formed a shell, the heavens enclosed everything. There was, at least in principle, an outside, even if no one knew what it contained. But once the idea of a perfect, unchanging sky began to loosen, it opened the door to a different kind of question. What if there is no edge at all? What if the stars are not attached to a surface, but instead scattered through a space that simply continues? It is a quiet leap, but a profound one. In the years following the appearance of that mysterious new star, a small number of thinkers began to explore this possibility. Among them was a man named Thomas Digges, who lived in England during the 16th century. Digges was deeply influenced by earlier ideas that had already begun to shift humanity's understanding of the cosmos. The Earth was no longer seen as the centre of everything. The Sun had taken that place, with the planets, including our own, moving gently around it. But Digges looked at the model of the universe that existed at the time and saw something that did not quite fit. In the traditional view, even with the Sun at the centre, the stars still formed a fixed outer shell, a boundary, a final layer that enclosed the entire system. And yet, if the heavens were not perfect and unchanging, if new stars could appear, then perhaps this outer shell was not real. Perhaps it was only an illusion. So Digges made a bold and surprisingly simple change. He imagined taking that outer shell of stars and removing it. Not replacing it with something else, not reshaping it, simply letting it go. And then, instead of placing the stars on a surface, he allowed them to drift outward, in all directions, not stopping at some distant boundary, but continuing further and further and further still, into a space that has no clear end. If you try to picture it, it may feel a little strange at first. There is no enclosing sphere, no final wall, just stars scattered across an immense expanse, each one separated by vast distances, yet all part of the same continuous reality. In this view, the universe is not a room with walls. It is more like an open landscape that stretches beyond the horizon, no matter how far you travel. And in that landscape, the Earth is no longer at the centre in any meaningful way. It is simply one location among many, one small vantage point within something far larger. There is a quiet shift in perspective here. The universe is no longer something arranged around us. We are something within it. This idea did not arrive with overwhelming force. It did not immediately replace the older models. In fact, for many people, it was difficult to accept. because it asks something quite subtle of the mind. It asks you to let go of boundaries, to imagine space not as a container, but as something that simply exists without edges or limits. And while that might sound abstract, you can feel a hint of it even in everyday experience. If you stand in an open field and look toward the horizon, it may seem as though the world ends there. But as you walk forward, the horizon moves with you. It never quite arrives. It is not a boundary, but a limit of perception. In a similar way, the idea of an infinite universe suggests that what we see is not the full extent of reality, but only the portion that is visible from where we stand. There is always more beyond, more stars, more space, more distance than we can easily imagine. But with this new picture comes a quiet problem, because if the universe truly is infinite and filled with stars, then something does not quite add up. If there are stars in every direction, extending endlessly, then every line of sight from Earth should eventually meet the surface of a star. No matter where you look, your gaze should end on something bright. The sky in that case should not be dark, it should glow, softly perhaps, or intensely, but it should be filled with light from every direction, layered upon itself across unimaginable distances. And yet, when we step outside at night, that is not what we see. We see darkness, deep, quiet darkness, punctuated by points of light. This contrast between what we might expect from an infinite universe and what we actually observe creates a gentle tension. A question that does not have an immediate answer, and like many such questions, it lingers. It sits quietly in the background, waiting. Because solving it will require something more than imagination alone. It will require a deeper understanding of how light travels, how far it can go, and how the universe itself behaves over time. But for now, the important shift has already taken place. The universe has expanded, not physically, not yet, but conceptually, from a finite shell to an open, unbounded space, from something enclosed to something that may have no edge at all. And within that vastness, the Earth becomes quieter, smaller, less central, but perhaps, in a gentle and unexpected way, more remarkable. Because from this small, unassuming vantage point, we have begun to glimpse the true scale of everything, not by travelling outward, but by thinking carefully about what we see, and by allowing even the most comfortable ideas to slowly, quietly change. By now, a quiet transformation has taken place. The universe is no longer imagined as a closed protective shell. The stars are no longer fixed to a distant surface. Instead, they are scattered through a vast, possibly endless space, stretching far beyond anything the eye can see. It is a beautiful idea, open, expansive, free of boundaries, and yet, like many beautiful ideas in science, it carries within it a small, almost hidden contradiction, a gentle tension that only becomes visible when you pause and think just a little more carefully about what this infinite universe truly implies. Imagine yourself again beneath a clear night sky. The air is still, the stars are steady. You look upward and your gaze moves across the darkness, settling here and there on individual points of light. Now consider this. If the universe is filled with stars, not just a few, not just billions, but an unending number of them, extending infinitely in every direction, then no matter where you look, your line of sight should eventually encounter a star. It may take a long distance, it may take a very long distance, but in an infinite universe, that distance is always finite. There's always another star waiting somewhere along the path of your gaze, and if that is true, then something surprising follows. Every direction you look should end, eventually on the surface of a star, not just occasionally, not just in certain parts of the sky, but everywhere. The night sky, in that case, should not appear dark between the stars. Instead, it should be filled continuously with light. Every small patch of darkness should be replaced by the faint glow of distant starlight, layered over itself again and again across immense distances. The sky should glow, softly perhaps, or intensely, but unmistakably. And yet, when you look up, that is not what you see. You see darkness, deep, calm darkness stretching between the stars. It is so familiar, so ordinary, that it rarely feels like something in need of explanation. But in the context of an infinite universe, it becomes a quiet mystery. Why is the sky dark? This question came to be known much later as a paradox, a situation in which two reasonable ideas seem to lead to a contradiction. On one hand, the universe might be infinite and filled with stars. On the other hand, the night sky is mostly dark. Both of these statements feel natural, and yet, together, they do not quite fit. To understand the tension more gently, you can imagine a simple scene. Picture yourself standing in a dense forest, surrounded by trees in every direction. If the forest extends far enough, then wherever you look, your view will eventually be blocked by a tree. Even if the trees are spaced apart, the sheer number of them ensures that your line of sight cannot travel forever without encountering something solid. Now replace each tree with a star. If the universe is like that forest, endless and filled with stars, then your view of the sky should be similarly filled. There should be no empty gaps, no open darkness, only layers of distant light. But the real sky does not behave like that forest. It feels more like standing in a field at night where the darkness dominates and the stars are scattered points of brightness within it. This difference is subtle, but profound, and for a long time there was no clear answer. Some early thinkers suggested that perhaps the stars were not distributed evenly. Maybe there were large empty regions between them. Others imagined that distant stars might somehow be dimmed or obscured before their light could reach us. These ideas carried a certain appeal, but they did not fully resolve the problem. Because even if the stars are spread out unevenly, an infinite universe still contains an infinite number of them. And even if some light is absorbed along the way, there is still an unending supply of starlight to replace it. The contradiction remains, and so the question lingers, not loudly, not urgently, but persistently. Why is the sky dark? What is it about the universe that allows darkness to exist at all? At this point in the story, the tools needed to answer this question do not yet exist. There are no precise measurements of distance between stars, no understanding of how light behaves over vast spans of time, no knowledge of whether the universe has a beginning or whether it has always existed. All that exists is the question itself, and sometimes in science that is enough. Because a good question has a way of guiding future discovery. It shapes the direction of inquiry. It quietly points toward what is missing in our understanding. In this case, the darkness of the night sky is not just an absence of light. It is a clue, a hint that something about the universe is not as simple as it first appears. Perhaps the universe is not truly infinite in the way we imagine. Perhaps it has not existed forever. Perhaps light does not travel across it in the way we expect. Or perhaps something even more subtle is at work. For now, these possibilities remain open. But what is clear is that the idea of an infinite static universe, unchanging and eternal, cannot fully explain what we see. And so, slowly, gently, the search for a deeper understanding continues. It will lead us to new tools, new methods of measurement, new ways of thinking about distance, time, and space itself. Because to solve the mystery of the dark sky, we will need to learn not just where the stars are, but how far away they truly lie, and that, it turns out, is a far more delicate question than it first appears. As the quiet question of the dark sky lingers, another challenge begins to take shape. If we are to understand the universe, we must first learn how to measure it, not in a hurried or forceful way, but patiently, carefully, with the kind of attention that builds understanding one small step at a time. Because when you look up at the night sky, it does not offer its distances freely. The stars do not come labelled with how far away they are. They do not grow larger as they move closer, or smaller as they move away, at least not in any way the eye can easily detect. To us they appear almost uniform, flat, like points drawn on a surface, and so, before we can answer the deeper questions about size, structure, or origin, we must first solve something much more basic. How far away are the stars? In the late 18th century, a man named William Herschel set out to explore this question in a way no one had attempted before. Herschel was not at first a professional astronomer. He began his life as a musician, someone attuned to rhythm, harmony, and careful practice. But over time, his curiosity turned toward the sky, and with it came a quiet determination to see further than anyone had seen before. Without access to ready-made instruments, he began to build his own telescopes. You can imagine the process as something both delicate and demanding, shaping metal into mirrors, polishing their surfaces until they could reflect the faintest traces of starlight. Night after night, refining the tools that would allow him to extend his vision deeper into the darkness. And slowly, as those instruments improved, the sky began to change, not in reality, but in perception. Where the naked eye saw scattered points of light, Herschel's telescopes revealed something richer, denser regions, faint clusters, subtle variations in brightness. The sky was no longer a simple pattern, but a textured landscape of stars. And so, he began a remarkable project. Instead of trying to measure the distance to each star individually, which at the time was beyond reach, he chose a different approach. He counted them, carefully, systematically, in different directions across the sky. Imagine standing in a large forest once again. If you cannot measure the distance to each tree, you might instead look around and notice how many trees appear in different directions. Where the forest is dense, you see many trunks close together. Where it thins out, the number decreases. From these patterns, you begin to form a sense of the forest's shape. Herschel applied a similar idea to the stars. By counting how many stars he could see in different parts of the sky, he hoped to infer the structure of the vast system they belonged to. And what he found was quietly extraordinary. In some directions, the stars appeared thick and numerous, forming a bright, hazy band across the sky. In others, they were more sparse. The pattern was not random. It suggested a shape, a flattened one, like a vast disk. This disk, Herschel proposed, was the structure of the system we now call the Milky Way galaxy, a great island of stars stretching far beyond the reach of the naked eye, with our own sun located somewhere within it. For the first time, humanity had begun to sketch a map of its cosmic home. Not a complete map, not a perfectly accurate one, but a meaningful step toward understanding the structure of the universe beyond our immediate surroundings. There is something quietly beautiful in this method, because Herschel did not leap to conclusions. He did not assume distances he could not measure. Instead, he worked with what he could observe, building a picture from patterns, from counts, from careful attention. And yet, as with many early efforts in science, his map carried an important limitation. Herschel assumed that his telescope allowed him to see all the stars within this great disk, that the boundaries he observed were in fact the edges of the system. But there was something he could not yet account for, something subtle but powerful. Between the stars there exists not only empty space, but also clouds of dust and gas. These clouds are not always visible, but they can gently absorb and scatter light, making distant stars appear dimmer or hiding them altogether. So when Herschel looked out into the denser regions of the galaxy, he was not seeing all the way through it. His view was, in a sense, softly obscured, like trying to look across a landscape through a thin veil of mist. And because of this, the map he created placed the Sun near the centre of the galaxy, not because it truly is, but because his observations were limited by what his instruments could reveal. Still, despite this limitation, the achievement remains remarkable. From a small planet using carefully crafted tools and patient observation, Herschel had begun to uncover the large-scale structure of the stars around us. The universe was no longer just a scattering of lights. It had form, it had shape, it had structure. But even as this picture came into focus, new questions began to emerge. Because scattered among the stars, Herschel and others observed faint cloud-like objects, soft patches of light that did not resolve into individual stars, even through powerful telescopes. These objects, known as nebulae, carried a quiet mystery. Were they simply clouds within our galaxy, or were they something more distant? Perhaps entire systems of stars in their own right? At this stage, there was no clear way to tell, because while Herschel had found a way to map the distribution of stars, he, and everyone else, still faced a deeper limitation. They did not yet have a reliable way to measure the true distances to objects far out in space, and without distance, the universe remains ambiguous, a flat pattern without depth, a map without scale. So as the 19th century drew to a close, the story reached a quiet pause. The shape of our galaxy had begun to reveal itself, but the true size of the universe remained just out of reach. And to go further, humanity would need to learn something new, not just how to observe the stars, but how to measure the space between them. As the picture of our galaxy slowly takes shape, as the stars begin to form a vast, gentle disk around us, something else begins to draw quiet attention, not the stars themselves, but the soft, mist-like patches that seem to float between them. If you imagine looking through a telescope on a clear night, scanning slowly across the sky, you might come across these faint, cloudy forms. They do not sparkle like stars. They do not resolve into sharp points of light. Instead, they appear as delicate smudges, like breath on glass, or distant fog illuminated by something unseen. These are what early astronomers called nebulae. The word itself simply means cloud, and at first, that is exactly what many believe them to be. Clouds of gas or unresolved clusters of stars drifting within the larger structure of the Milky Way. And for a while, that explanation felt sufficient. After all, Herschel had shown that the galaxy itself was vast, filled with countless stars. It seemed reasonable that within such a system there might also be regions where stars were too faint or too densely packed to distinguish individually. But there was something about these nebulae that did not quite fit. Some of them had structure, not random, shapeless clouds, but distinct forms, spiral patterns, symmetrical shapes, subtle hints of organization, as though they were not simply diffuse matter, but something more complex. If you let your mind rest on that image for a moment, a faint spiral of light, barely visible through a telescope, it carries a quiet suggestion that this might not be a cloud at all, but something larger, something composed of stars, just like our own galaxy. At this point in the story, however, there was no way to know for certain, because while astronomers could observe these nebulae, they still lacked one crucial piece of information: distance. Without knowing how far away something is, it becomes very difficult to understand what it truly is. A small nearby object can appear identical to a large distant one. A faint glow could be a modest cloud within our galaxy, or a vast system of stars located far beyond it. From our vantage point, the difference is not immediately visible, and so a quiet uncertainty begins to grow. Some astronomers continue to believe that the Milky Way was the entirety of the universe, that everything visible in the sky, stars, nebulae, clusters, belong to this single enormous structure. In this view, the universe was vast, but still contained. Others began to consider a more expansive possibility. What if these nebulae were not part of our galaxy at all? What if they were distant island universes, entire galaxies in their own right, scattered across an even larger cosmos? It is a remarkable idea, if you pause to feel it. Not just one galaxy, but many. Not just one island of stars, but countless islands, separated by immense stretches of space, each one with its own stars, its own structure, its own quiet story unfolding across time. But without a reliable way to measure distance, this idea remained just that, an idea. And so, the question lingered, are we looking at nearby clouds, or distant worlds? The uncertainty grew into what became known as a great debate, not a sudden or dramatic conflict, but a long, thoughtful disagreement among astronomers, each side working carefully, gathering observations, building arguments, and yet both perspectives had merit. Those who believed in a single galaxy could point to the apparent brightness and distribution of nebulae, suggesting they were relatively close. Those who favoured the idea of multiple galaxies could point to the shapes and structures within some nebulae, which seemed too organised, too vast to be mere clouds. It is a reminder, perhaps, that in science the path to understanding is not always clear. Sometimes the evidence allows for more than one interpretation, and until a new method, a new tool, or a new insight emerges, the truth remains just out of reach. In this case, the missing piece was not a better telescope, not a clearer image, but a deeper way of measuring distance. Because if you could determine how far away one of these nebulae truly was, the answer would become clear. If it lay within the boundaries of the Milky Way, then it was part of our galaxy. But if it was far beyond those boundaries, then it must be something else entirely. A separate system, a galaxy of its own. And so, quietly, the focus begins to shift, from mapping the stars to measuring the space between them, from observing patterns to understanding scale, because only by learning how to measure vast distances can we begin to see the universe in 3 dimensions, not as a flat pattern of lights, but as a deep layered structure extending outward in all directions. At this moment in our story, the answer has not yet been found. The nebulae remain mysterious, the universe remains uncertain, but the direction forward is becoming clear. To move beyond this uncertainty, humanity will need to develop a new kind of tool. Not a physical instrument, but a method. A way to use the subtle shifts in perspective, the gentle movement of the Earth itself, to measure distances across the vastness of space. It is a delicate idea, simple in principle, but profound in its implications. Because once we can measure distance, even in the smallest way, the entire scale of the universe begins to unfold, and what once seemed like a quiet sky of scattered lights begins to reveal itself as something far deeper. There is a quiet kind of difficulty that comes with distance, not the kind you feel when walking across a room or travelling between cities, but something more subtle, more elusive, the kind of distance that cannot be reached, cannot be touched, and cannot be measured with ordinary tools. When you look up at the night sky, every star, no matter how far away, appears as a small point of light. There is no obvious sense of depth, no visual cue that tells you which stars are nearby and which are unimaginably distant. It is as though the universe presents itself as a flat canvas, and yet we know, or at least we begin to suspect, that this cannot be the full story. Because if the nebulae are to be understood, if we are to decide whether they belong to our galaxy or lie far beyond it, then we must find a way to measure distance. Not just guess it, not infer it loosely, but measure it in a way that is careful, repeatable, and grounded in observation. And to do that, astronomers turn to something very familiar: motion. More specifically, they turn to the gentle motion of the Earth itself. If you imagine holding your hand out in front of you and then slowly shifting your position, perhaps moving your head slightly from side to side, you may notice something subtle. Your finger seems to shift against the background behind it. It appears to move, even though it is staying in the same place. This effect becomes even clearer if you compare two objects, one close to you and one far away. The closer object appears to shift more. The distant object appears almost still. This simple observation carries a quiet but powerful idea. By measuring how much an object appears to shift when viewed from two different positions, you can estimate how far away it is. Closer objects shift more, distant objects shift less. This effect is known as parallax, and while it is easy to observe in everyday life, applying it to the stars required patience, precision, and time, because the shift in position of even the nearest stars is incredibly small. To make the effect measurable, astronomers needed to observe stars from two positions that were as far apart as possible, and the Earth, in its slow journey around the Sun, provided exactly that opportunity. 6 months apart, the Earth finds itself on opposite sides of its orbit. The distance between these two positions is vast on a human scale, stretching across hundreds of millions of kilometers. From these two vantage points, astronomers could observe a star and look for a tiny shift in its position against the more distant background. If such a shift could be detected, then, in principle, the distance to the star could be calculated. It sounds simple, but in practice, it was anything but. The stars are so far away that their apparent movement is almost imperceptible. It is like trying to detect the motion of a distant mountain by shifting your position by a few steps. The change is there, but it is extremely subtle. For many years, astronomers searched for this effect without success. It was not until the 19th century that a man named Friedrich Bessel succeeded in measuring it for the first time. He focused on a relatively nearby star and, through careful observation, detected the tiny shift in its position over the course of a year. From that shift, he was able to estimate the star's distance. The results astonishing. The star was not just far away, it was unimaginably distant. So distant that light itself, travelling at incredible speed, would take years to cross the space between that star and Earth. This realization carries a quiet kind of weight, because it transforms the stars from points on a distant surface into objects separated by vast empty spaces. The universe begins to gain depth. It is no longer a flat pattern, but a three-dimensional expanse. And yet, even as this method opened a new window into the cosmos, it came with a limitation. A gentle boundary, defined not by theory, but by practicality. The parallax effect becomes smaller as distance increases. For stars that are very far away, the shift becomes so tiny that it cannot be measured even with the most careful observations available at the time. It is as though the universe reveals its nearby structure, but keeps its more distant regions hidden. You might think of it like standing in a large, dimly lit hall. Nearby objects are easy to see, their positions are clear, their distances can be judged. But as you look further into the darkness, the details begin to fade, shapes become indistinct, distances become uncertain. Parallax allowed astronomers to measure the nearby stars, but beyond a certain point, it could no longer reach. And so, while this method marked a profound step forward, it did not yet solve the deeper problem. It didn't tell us how far away the nebulae were. It didn't reveal whether they lay within our galaxy or far beyond it. It provided the first rung on a ladder, but the ladder itself would need to extend much further. Still, there is something quietly beautiful in this achievement, because with nothing more than careful observation and the gentle motion of the Earth, humanity had found a way to measure distances across the vastness of space, not by travelling there, not by reaching out, but by watching, patiently. As the perspective shifted ever so slightly over time, it is a reminder that even the smallest changes, when understood deeply, can reveal something immense. And as this understanding settles in, the path forward becomes clearer. If parallax can measure nearby stars, then perhaps there is another method, one that can reach further, a method that does not rely on tiny shifts in position, but on something else. Something built into the stars themselves, a pattern, a rhythm, a subtle signal that carries information about distance, even across the deepest stretches of space, and as the search continues, that signal will soon be found. Not in the motion of the Earth, but in the quiet pulse of certain stars, blinking steadily in the darkness. There is a quiet rhythm hidden in the universe, not one you can hear, not one you can feel directly, but one that reveals itself slowly, patiently, to those who take the time to watch. Up to this point, the story has been guided by motion, the gentle shifting of perspective, the movement of the Earth allowing us to glimpse the depth of nearby space. Through that motion, we learned how to measure the distance to stars that lie relatively close to us. But beyond that, the universe still remained distant and uncertain. The nebulae, those soft clouds of light, still held their mystery. Parallax had given us a beginning, but not yet a way forward. And so, the question lingered: how do you measure something that is too far away to shift? How do you reach across distances so vast that even the motion of the Earth is no longer enough? The answer, when it came, didn't arrive through force or speed, but through pattern. A quiet, repeating pattern, hidden within certain stars themselves. At the turn of the 20th century, a remarkable observer named Henrietta Leavitt was working at an observatory, studying photographic images of the night sky. Her task, at least on the surface, seemed straightforward. She examined plates of glass imprinted with images of stars, comparing them carefully, noting changes, cataloguing details. But within this steady, patient work, she began to notice something unusual. Some stars did not shine with constant brightness. Instead, they seemed to pulse, bright, then dim, then bright again, over and over in a steady rhythm. At first glance, this might seem like a small curiosity, a minor variation in behaviour among many thousands of stars. But Leavitt noticed something deeper. The rhythm of these stars, the time it took for them to brighten and dim, was not random. It followed a pattern. Some stars pulsed quickly, completing their cycle in a short time. Others pulsed more slowly, taking longer to move from bright to dim and back again. And then came the quiet realization that would change everything. The stars that pulsed more slowly were, in fact, brighter, not just as they appeared from Earth, but in their true nature. They emitted more light, while the faster pulsing stars were dimmer by comparison. This relationship between rhythm and brightness is subtle, but incredibly powerful. Because if you know how bright something truly is, and you compare that to how bright it appears, you can begin to understand how far away it must be. You can imagine it like this. If you see a lamp glowing softly in the distance, it might appear dim. But if you know that the lamp is actually very bright, then its faint appearance tells you that it must be far away. On the other hand, if the lamp is small and weak, then even a dim glow might mean it is quite close. In the same way, these pulsing stars, known today as Cepheid variables, act like cosmic lighthouses. Their rhythm tells us their true brightness, and once we know that, we can compare it to what we see from Earth and gently infer their distance. It is a remarkably elegant method. No need for shifting perspectives, no need for measuring tiny angles, just a careful observation of light and time. And yet, what makes this discovery even more profound is what it allows us to do next. Because unlike parallax, which is limited to nearby stars, this method can reach much further, far beyond the immediate neighbourhood of our solar system. Far enough, in fact, to begin measuring distances across the entire galaxy and even beyond. With this new tool, astronomers were no longer confined to the nearest stars. They could begin to explore the deeper structure of the cosmos, to measure objects that had previously been out of reach. And among those objects were the mysterious nebulae. For the first time, there was a way, at least in principle, to determine how far away one of these faint cloud-like forms truly was. If a Cepheid variable could be found within a nebula, and its rhythm carefully measured, then its distance could be calculated, and with that distance, the true nature of the nebula would finally be revealed. Close or distant, part of our galaxy, or something entirely separate. It is a quiet turning point in the story, because the question that once seemed philosophical about the size of the universe, about the nature of these distant clouds, was becoming measurable, not through speculation, but through observation, pattern, and careful reasoning. There is something deeply calming in this approach. It does not rush toward answers, it does not force conclusions, it simply listens to the rhythm of the stars, and from that rhythm it builds understanding. At this moment, the universe is still on the verge of revealing its true scale. The tools are now in place, the methods are ready. All that remains is for someone to look carefully at one of those distant nebulae and find within it the quiet pulse of a Cepheid star. And when that happens, the boundaries of the universe will shift once again, not suddenly, not dramatically, but in a way that gently expands everything we thought we knew. Because sometimes the key to measuring the largest distances in existence comes from something as simple and as steady as a heartbeat of light. By now, something quiet but powerful has taken shape. We have learned how to measure nearby stars using the gentle shift of perspective. We have discovered a deeper method, hidden in the steady pulse of certain stars, allowing us to reach far beyond those nearby distances. The tools are ready, the methods are in place, and all that remains is a moment of observation. A moment when someone looks carefully enough, patiently enough, to bring all of these ideas together. In the early 20th century, that moment arrived through the work of Edwin Hubble. Hubble was, in many ways, a different kind of astronomer. He worked at a time when telescopes had grown far more powerful, capable of gathering faint light from distant parts of the sky that earlier observers could not reach. These instruments did not simply reveal more stars, they revealed structure, depth, subtle variations in brightness and form. And among the many objects Hubble studied was one of the most intriguing of all, a faint, spiral-shaped nebula in the constellation Andromeda. To earlier astronomers, this object had been just that, a nebula, a cloud-like patch of light, unresolved and uncertain. But now, with more powerful tools and a deeper understanding of stellar behaviour, it carried a new possibility. If Andromeda contained a Cepheid variable star, then its distance could be measured. And so, with careful observation, Hubble searched, night after night examining photographic images of the nebula, looking for subtle changes in brightness, watching for the telltale rhythm of a star that pulses in time, and eventually he found it. A single star embedded within that faint spiral, gently brightening and dimming in a steady pattern. It may not have seemed like much at first, just one star among many. But within that quiet pulse was the key to an enormous question. Hubble measured its rhythm. He compared that rhythm to what was already known about such stars, the relationship between how quickly they pulse and how bright they truly are. And from that he inferred its distance. The result was not just surprising, it was transformative. The star was far too distant to belong to the Milky Way, not just slightly beyond its edge, but vastly beyond it. So far away that the entire nebula it resided in could not possibly be part of our galaxy. It had to be something else, an entire galaxy of its own. A vast collection of stars similar in scale to the Milky Way, but located millions of light years away. In that moment, the universe quietly changed. What had once been thought of as a single galaxy, the entirety of existence, was now understood to be just one among many. The cosmos expanded, not physically, not yet, but conceptually. The boundaries of the known universe moved outward, not by a small margin, but by an unimaginable amount. If you pause and let that idea settle, it carries a gentle kind of astonishment. Because until that point, the Milky Way had been everything, every star, every nebula, every visible object in the sky, and suddenly it became just one island in a vast ocean of galaxies, each one separated by distances so large that even light, travelling at incredible speed, takes millions of years to cross the space between them. And this brings with it another quiet realization. When you look at a distant galaxy like Andromeda, you're not seeing it as it is now. You're seeing it as it was, because the light reaching your eyes has been travelling for millions of years. It began its journey long before modern humans existed, long before recorded history, long before the world as we know it had taken shape. In a sense, every distant object in the universe is a glimpse into the past. The further away something is, the longer its light has travelled, and the older the image we receive. The universe becomes not just a place, but a story unfolding across time, a layered history, written in light. And Hubble's discovery opened the door to reading that history on a much larger scale. Because if there are many galaxies, then the universe is not just larger than we thought. It is structured, organised, filled with systems that extend far beyond our own. But even as this new picture began to settle in, it carried with it a deeper question. If galaxies exist at such vast distances, how are they arranged? Are they scattered randomly? Do they move? Does the universe itself change over time? These questions linger quietly at the edge of understanding, because discovering that the universe is vast is only the beginning. Understanding how it behaves, how it evolves, is a different kind of challenge altogether, and to explore that, astronomers would need to look not just at where galaxies are, but at how they move. Because hidden within that motion, within the subtle stretching of light across space, is the next great revelation. A realization that the universe is not static, not fixed, but slowly, gently, expanding. And with that realization, the story will shift once again, from a universe that simply exists to one that is changing, moment by moment, across the vastness of time. As the universe quietly expands in our understanding, as galaxies reveal themselves as distant islands of stars, a new kind of question begins to emerge, not about where things are, but about what space itself truly is. Up to this point, space has felt almost invisible, a silent stage upon which everything else moves. Stars drift through it, galaxies float within it, light travels across it, but space itself has remained in the background, unquestioned, taken for granted. If you imagine the room around you right now, it likely feels simple: straight walls, flat surfaces, corners that meet cleanly, distances that behave in familiar ways. If you draw a straight line from one point to another, you expect it to be the shortest path. If you draw a triangle, you expect its 3 angles to fit together in a neat, predictable way. These expectations are not random. They come from a way of thinking about space that has been with us for a very long time, a way that was carefully described over 2,000 years ago by Euclid. Euclid's ideas were simple, elegant, and deeply intuitive. In his view, space was flat. Lines extended smoothly and endlessly. Parallel lines would never meet. Shapes behaved in consistent and predictable ways. It was a kind of geometry that matched everyday experience so perfectly that it felt not just useful, but true. Not just mathematically true, but physically true. For centuries, people believed that this was simply how space worked. Everywhere, without exception, and for most purposes it worked beautifully. You can still feel this intuition in your own experience. If you walk across a flat surface, the shortest path between 2 points feels like a straight line. If you look at a rectangular window, its edges appear parallel, never drifting closer or further apart. Everything seems stable, reliable, calm. But there's a subtle assumption hidden within this picture, an assumption that space behaves the same way everywhere, no matter how large the scale. And it is precisely this assumption that begins to soften as our view of the universe expands. To sense why, it helps to step away from flat surfaces for a moment and imagine something slightly different. Imagine standing on the surface of a perfectly round sphere. Not a small one that you can see all at once, but something vast, so large that it feels flat beneath your feet. Something like the surface of the Earth itself. Now imagine drawing a straight path across that surface. If you begin walking forward, always moving in the same direction, you might feel as though you're travelling along a straight line, and in a sense, you are. But if you continue long enough, something unexpected happens. You eventually return to where you started, not because you turned around, but because the surface itself is curved. Your straight path has quietly followed that curvature. Now imagine drawing a triangle on this surface, one corner at the North Pole and 2 others somewhere along the equator. If you trace the edges carefully, you will find something surprising. The 3 angles of this triangle do not fit together in quite the same way they would on a flat surface. They add up to more than you might expect, not dramatically more, but enough to reveal that something is different. Something subtle has changed, and that change is not in the triangle itself, but in the space it is drawn upon. This is the first gentle hint that the rules we take for granted, the ones that feel so natural and intuitive, may not apply everywhere. They work beautifully on small scales in familiar environments, but on larger scales, or in different kinds of space, they begin to bend, not break completely, but soften, adapt, shift in ways that are not immediately obvious but deeply meaningful. And once this idea takes hold, even lightly, it begins to open new possibilities. What if space is not perfectly flat? What if the geometry we experience in everyday life is only an approximation? a local version of something more complex? What if, on the larger scales of the universe, the very fabric of space behaves differently? These questions do not demand immediate answers. They simply invite a new way of looking. A way that does not assume that straight lines are always straight, or that parallel paths remain forever separate. Instead, they suggest that space itself might have a kind of shape, a structure, a gentle curvature that reveals itself only when we step back far enough to see it. And at this point in our story, that idea is still forming, still quiet, still waiting for someone to take it further. Because recognizing that curved surfaces behave differently is only the beginning. The deeper question is more challenging. What if space itself, not just surfaces within it, but the very space we live in, can be curved, not bent within some higher dimension that we can step outside of, but curved from within, experienced directly, even if we cannot easily see it. It is a subtle shift, but one that will soon lead to a profound change in how we understand the universe. Because once space is allowed to bend, everything that moves within it begins to follow new paths that may still feel natural, but are guided by something deeper than simple geometry, something woven into the structure of space itself. As the idea begins to settle that straight lines may not always behave the way we expect, a quieter, deeper question starts to form beneath it. If surfaces can be curved, if paths can bend without us noticing, then what about space itself? Not the surface of a sphere, not the outside of an object, but the very space we live in. The invisible background that holds everything, the stars, the galaxies, even ourselves. Can that be curved too? It is a difficult idea to approach at first, not because it is complex in a technical sense, but because it asks something unusual of our intuition. We're used to thinking about shapes by stepping outside them. We look at a ball and see its curve. We look at a hill and notice its slope. We understand curvature by comparison, by seeing how something bends relative to the space around it. But what if there is no outside? What if the thing that is curved is the space itself? To gently approach this idea, imagine once again a tiny traveller, an ant, perhaps, walking slowly across the surface of a vast sphere. The sphere is so large that the ant cannot see its edges. To the ant, everything feels flat. The ground beneath its feet seems smooth and endless. There are no visible curves, no obvious boundaries. If the ant begins to walk forward, it believes it is moving in a straight line, and in its own experience, it is. There is no sense of turning, no awareness of bending. It simply continues, step by step, across what feels like an infinite surface. And yet, if it keeps walking long enough, it will return to where it started. Not because it changed direction, but because the space it moved through was curved all along. Now imagine that the ant begins to explore more carefully. It draws shapes, it marks paths, it tries to understand the rules of the space it inhabits. At first, everything seems familiar. Small triangles behave as expected, short distances appear flat. The world makes sense. But as the ant expands its measurements, creating larger and larger shapes, it begins to notice something subtle. The rules it thought were universal begin to shift. The angles of a large triangle feel just slightly different. Paths that should remain parallel slowly drift together. Nothing dramatic, nothing abrupt, just a gentle deviation from expectation. And from these small differences, the ant might begin to suspect something profound, that the space it lives in has a shape, even if it cannot step outside to see it. This idea, in a more careful and mathematical form, was explored by thinkers like Carl Friedrich Gauss and later expanded by Bernhard Riemann. They began to ask whether the geometry of space could be understood from within, without needing an external viewpoint. Their insight was quiet but powerful. You do not need to step outside a space to understand its shape. You can discover its curvature by observing how things behave inside it, how lines move, how shapes form, how distances relate. In other words, the shape of space reveals itself through experience. This shift in thinking is subtle, but it changes everything. Because it allows us to consider that the universe itself might have a kind of geometry, one that is not necessarily flat, not necessarily infinite in a simple way, but structured in a manner that can be explored from within. At this point, the idea is still abstract. There are no immediate consequences, no dramatic changes in how we see the stars or measure their distances. It is more like a quiet rearrangement of possibilities, a soft expansion of what space is allowed to be. But ideas like this tend to linger. They settle into the background of thought, waiting for the right moment to become something more. And that moment arrives when someone takes this abstract notion of curved space and connects it to something very real, something we experience every day: gravity. Because until now, gravity has been understood in a very straightforward way. Objects attract one another. A force pulls things together. Apples fall. Planets orbit. The explanation feels simple, almost mechanical. But what if that explanation is only part of the story? What if gravity is not just a force acting within space, but a consequence of space itself being shaped? It is a gentle idea, at first, almost easy to overlook. But once it is fully explored, it transforms the way we understand motion, distance, and the universe as a whole. Because if space can curve, and if objects move naturally along the paths defined by that curvature, then what we perceive as attraction might actually be something else entirely. Not a pull, but a path, a quiet following of the shape of space itself. At this point in the journey, the pieces are beginning to align. We have learned that the universe is vast, that it contains countless galaxies, that distances can be measured, and that light carries information across time. Now we begin to see that the stage upon which all of this unfolds, space itself, is not as simple as it once seemed. It is not just an empty backdrop. It has structure, it has shape, and perhaps most intriguingly of all, it can change. And as that realization deepens, it leads naturally to the next step. Because once space is allowed to bend, the motion of everything within it begins to take on a new meaning, a meaning that will soon be revealed through one of the most profound insights in the history of science, an insight that does not just describe gravity, but redefines it entirely. By now, a quiet shift has taken place. Space is no longer just an empty stage. It is no longer something passive, something that simply exists while everything else moves within it. Instead, it has begun to feel more active, more structured, something that can bend, stretch, and quietly shape the paths of everything inside it. And if you let that idea rest for a moment, something interesting begins to follow. If space has a shape, then motion within that space might not require a force in the way we once imagined. It might simply follow the shape that is already there. For a long time, gravity had been understood in a very direct way. Objects attract one another. A force pulls them together. If you drop something, it falls. If you throw something upward, it slows, stops, and returns. It is simple, predictable, familiar, and in many ways this understanding works remarkably well. But there is a quiet question hidden within it. What exactly is this force? How does the Earth reach out and pull an object toward it? How does the Sun hold the planets in their paths without any visible connection? For centuries, these questions remained in the background. The equations describing motion were precise and reliable. even if the deeper explanation was not fully clear. And then, in the early 20th century, a new way of thinking began to take shape through the work of Albert Einstein. Einstein approached the problem from a different angle. Instead of asking how objects pull on one another across space, he asked something simpler, and in some ways, more subtle. What if there is no pulling at all? What if objects move the way they do because of the shape of space itself? To begin to feel this idea, imagine placing a small object on a smooth, stretched surface, like a fabric pulled tightly in all directions. If the surface is perfectly flat, the object will remain where it is. There is no reason for it to move. But now imagine placing something heavy in the center of that surface. The fabric begins to dip, forming a gentle curve. If you then place a smaller object nearby, it will begin to move, not because it is being pulled by an invisible force, but because the surface beneath it is no longer flat. It follows the slope, drifting inward along the curved path. From a distance, it may look as though one object is pulling the other, but from within the system, what is really happening is simpler. The objects are following the shape of the surface. Einstein's insight was that something like this might be happening in the universe itself. Not with a physical fabric, of course, but with space and time woven together into a single structure. Massive objects like stars and planets do not just sit within space, they shape it. They create gentle curves in the fabric of space-time, and other objects move along those curves naturally. What we experience as gravity is not a force pulling things together, but the natural motion of objects following the geometry of the space they inhabit. It is a subtle shift in perspective, and yet it changes everything. Because it means that when the Earth orbits the Sun, it is not being pulled in the traditional sense. It is moving along a path defined by the curvature created by the Sun's presence. When an apple falls, it is not being reached for by the Earth. It is simply following the path that space itself provides. This idea may feel abstract at first, but it carries a quiet elegance. It removes the need for invisible forces acting at a distance. It replaces them with something more continuous, more woven into the structure of reality itself. And perhaps most importantly, it allows us to connect gravity with the geometry we have already begun to explore. Curved space is no longer just a mathematical curiosity. It becomes something physical, something that shapes motion, light, and time. And as this idea settled into the scientific world, it began to reveal new and unexpected consequences. Light, for example, does not simply travel in straight lines through empty space. It follows the curvature as well. If it passes near a massive object, its path bends slightly, curving along the shape of space-time. This means that even something as fast and seemingly untouchable as light is guided by the structure of space. Time, too, is affected. Clocks placed in stronger gravitational fields tick more slowly than those in weaker ones. The flow of time itself becomes part of the geometry, subtly shifting depending on where you are. These effects are gentle, almost imperceptible in everyday life, but on cosmic scales they become significant. They shape the paths of stars, the motion of galaxies, and the behavior of light traveling across the universe. And with this new understanding, the stage is set for an even deeper realization. Because if space and time can be curved, if massive objects can shape that curvature, then the universe itself is no longer static. It is no longer fixed in a single, unchanging form. Instead, it becomes something dynamic, something that can evolve, expand, change over time. At this point in our journey, we have not yet seen that change directly, but the possibility is now there. Hidden within the equations that describe space-time, within the gentle curvature that guides motion, lies the suggestion that the universe may not remain still, that it may in fact be in motion on the largest scale imaginable. And as this idea begins to unfold, it will lead to one of the most profound shifts in our understanding of the cosmos. A realization that the universe is not only vast, but alive with change, quiet, slow and almost imperceptible, but constant, a universe that does not stand still, but slowly, gently, grows. With this new understanding, something subtle begins to shift. Space is no longer passive, time is no longer separate. Together they form a single fabric that can bend, curve, and guide the motion of everything within it. Gravity is no longer a mysterious pull, but a quiet expression of that curvature. And if you let that idea settle gently, another question begins to emerge. If space and time can bend, can they also change? Not just locally, not just around stars or planets, but on the largest scale of all. Can the universe itself evolve? When Albert Einstein first explored the equations describing space-time, he found something unexpected. The mathematics didn't naturally describe a universe that remained still. Instead, they suggested a universe that could expand, or contract, or change over time in subtle but profound ways. This result was, in a quiet sense, unsettling, because at the time, the prevailing belief was that the universe was static, unchanging on the larger scales, eternal in its structure. Even though earlier observations had begun to challenge that idea, the notion of a steady, balanced universe still felt deeply intuitive. And so, Einstein did something that, in hindsight, carries a very human quality. He adjusted the equations, not in a careless way, but gently, deliberately, adding a small term, a kind of balancing influence, designed to hold the universe in a stable state. This addition is often described as a cosmological constant, though you can think of it simply as a subtle adjustment meant to prevent large-scale change. It is like adding a gentle counterweight to a system that would otherwise begin to drift. With this adjustment, the equations could describe a universe that neither expands nor contracts, a universe that simply exists, balanced and still. For a time, this seemed like a reasonable solution. After all, if the universe appears stable, then perhaps it truly is. But there is a quiet tension in forcing a system to remain still when its natural behaviour suggests movement. And as new observations began to emerge, that tension became harder to ignore. Astronomers were no longer limited to studying stars within the Milky Way. They had begun to observe distant galaxies, each one a vast collection of stars moving through space. And as they examined the light from these galaxies more closely, they noticed something subtle, something that at first might have seemed like a small detail, but would soon carry enormous significance. The light from many distant galaxies appeared slightly shifted, not randomly, not unpredictably, but consistently in a particular direction. To understand this shift, it helps to imagine something familiar. If you've ever heard the sound of a passing vehicle, a car or a train, you may have noticed how its pitch changes as it moves. As it approaches, the sound waves are compressed and the pitch seems higher. As it moves away, the waves stretch out and the pitch becomes lower. Light behaves in a similar way. When an object emitting light moves toward us, the light waves become slightly compressed. When it moves away, they stretch out, becoming longer and softer. This stretching of light, this gentle shift toward longer wavelengths, can be thought of as a kind of reddening, since longer wavelengths correspond to redder light. And when astronomers observed distant galaxies, they found that many of them showed this kind of shift. Their light was stretched, gently, consistently, stretched, as if they were moving away. At first, this might not seem surprising. Perhaps galaxies simply move through space in different directions, some approaching, some receding. But as more observations were gathered, a pattern began to emerge. The further away a galaxy was, the more its light appeared to be stretched, not randomly, not occasionally, but in a steady, almost rhythmic relationship, distance and stretching, linked together. This pattern suggested something deeper than simple motion. It hinted that the space between galaxies itself might be changing. Not that galaxies were flying outward through a fixed space, but the space itself was expanding, carrying galaxies along with it. To picture this, you might imagine small dots drawn on the surface of a slowly inflating balloon. As the balloon expands, the dots move further apart, not because they are moving across the surface, but because the surface itself is growing. From the perspective of any single dot, it appears as though all the others are drifting away, and the further away they are, the faster that separation seems to occur. This is a gentle but profound shift in perspective. The universe is not expanding into something else. It is expanding as itself. Space is growing, distances are increasing, and this expansion is not something that happens in one region or another. It is a property of the universe as a whole. At this point, the earlier idea of a perfectly balanced, unchanging universe begins to feel less certain. The equations that once suggested movement now seem to align with observation, and the small adjustment that was added to keep the universe still begins to look less like a necessity and more like a temporary solution. Einstein himself would later reflect on this, describing his attempt to hold the universe static as a mistake, not because the idea was unreasonable, but because the universe, it seems, was never meant to stand still. It was always changing, always evolving, always moving, even if that motion is so slow, so vast, that it escapes immediate notice. And as this realization settles in, it opens the door to an even deeper question. If the universe is expanding now, what was it like in the past? If distances are growing, then long ago everything must have been closer together. And if we follow that idea gently backward, we begin to approach a moment when the universe was not vast and spread out, but small, dense, and tightly connected. A beginning, perhaps, not a sudden explosion in space, but a state from which space itself began to unfold. And as that possibility begins to take shape, the story moves quietly forward, from a universe that changes to a universe that has a history, a beginning, written not in words, but in the slow, steady expansion of space itself. As the idea of an expanding universe begins to settle in, it brings with it a quiet sense of movement, not the kind of motion we experience in everyday life, not objects rushing past one another or drifting through empty space in obvious ways, but something more subtle, more gentle, a slow widening, a quiet stretching of the distances between everything. If you imagine standing in a vast open field, watching distant landmarks move away from you, you might feel as though you're at the center of that motion, as though everything is receding from your position. But in the expanding universe, something more delicate is happening. It is not that we are at the center, it is that the space between galaxies is growing, and because of this, every observer, no matter where they are, would see the same pattern. Galaxies appear to drift away, in all directions, and the further away they are, the faster the separation seems to occur. This relationship between distance and motion is one of the most important discoveries in our understanding of the cosmos. It is often described in a simple way. The farther a galaxy is, the faster it appears to move away from us. But rather than thinking of it as motion through space, it is more helpful, more accurate, to think of it as the stretching of space itself. To feel this more clearly, you might imagine a long, flexible thread with small beads placed along it. If the thread is gently stretched, the beads move further apart. A bead that is twice as far away from you will move away more quickly as the thread stretches, simply because there is more space between you and it to expand. In this way, the motion is not something the beads are doing, it is something happening to the space between them. And this is how the universe behaves on its larger scales. Galaxies are not racing outward from a central point. They are being carried apart as space itself slowly grows. This idea may feel a little unfamiliar at first, because it does not match our everyday experience. In our daily lives, space feels fixed. Distances remain stable unless something moves through them. But on the scale of the universe, space itself is dynamic. It can stretch, it can expand, and as it does, it carries everything within it along for the journey. The evidence for this expansion comes from the light we receive from distant galaxies. As we touched on earlier, light behaves in a way that reflects motion. When something moves away, its light becomes stretched, shifting gently toward longer wavelengths. This stretching is not abrupt or dramatic. It is subtle, almost like a soft pulling of a thread, and yet when measured carefully it reveals a clear pattern. The light from more distant galaxies is stretched more. The light from nearer galaxies is stretched less. This smooth progression tells a quiet story, a story of space itself expanding, of distances growing over time, and of a universe that is not fixed, but evolving. There is something almost calming in this idea. The expansion is not violent, it is not chaotic, it is steady, gradual, measured. On human timescales, it is almost imperceptible. The distance between galaxies grows so slowly that you would never notice it in a lifetime, or even across many generations. And yet, over millions and billions of years, the effect becomes profound. Galaxies drift further apart. Clusters of galaxies become more isolated. The large-scale structure of the universe slowly stretches, like a pattern drawn on a surface that is gently being pulled outward. But even within this expansion, there are places where gravity still holds sway. Galaxies themselves remain intact. Stars continue to orbit within them. Smaller groups of galaxies can remain bound together, resisting the expansion on local scales. It is only across the vast distances between these structures that the stretching of space becomes dominant. This balance between the inward pull of gravity and the outward expansion of space creates a universe that is both connected and dispersing at the same time. A universe where structures form, evolve, and slowly drift apart. And as we begin to understand this motion more deeply, another quiet realization begins to take shape. If the universe is expanding now, then in the past it must have been smaller. Not just slightly smaller, but significantly so. Because if distances are increasing today, then long ago everything must have been closer together. Closer, denser, more tightly packed. It is a simple idea, but one that carries enormous implications. Because if you continue to follow this line of thinking backward, gently, without forcing it, you begin to approach a time when the entire universe was compressed into a much smaller region. Not a point in space, but a state of extreme density and temperature. A beginning, perhaps. Not in the sense of a sudden explosion into empty space, but as the starting condition from which space itself began to expand. This idea does not yet need to be fully formed. It can remain soft at the edges, a possibility rather than a conclusion. But it is a direction a path that emerges naturally from what we observe. And as we follow that path further, guided by light and motion and careful reasoning, we will begin to uncover evidence that supports this view. Evidence that the universe, as vast and ancient as it is, has a history, a past that can be traced, not through memory, but through the light that still travels toward us, carrying information from distant times. And within that light, there is a faint signal, a quiet glow, something that does not belong to any one star or galaxy, but to the universe itself, a remnant of an earlier state, still present, still surrounding us. And as we turn our attention toward that faint glow, the story of the universe's beginning begins to come into focus. Not sharply, not all at once, but slowly, gently, like something emerging from the darkness. As the idea of an expanding universe settles gently into place, it brings with it a quiet invitation. An invitation to look not only outward, but backward. Because if the universe is growing today, if the distances between galaxies are slowly stretching, then it is natural to imagine reversing that motion in your mind. Not quickly, not dramatically, but slowly, as though you're watching a long film and gently sliding it in the opposite direction. Galaxies that drift apart begin to move closer together. The vast spaces between them begin to shrink. Clusters of galaxies draw nearer. Patterns tighten. The large-scale structure of the universe, once spread across immense distances, begins to gather inward. And as you continue this gentle rewinding, something deeper begins to happen. The universe itself becomes smaller, not just in one region, not just locally, but everywhere at once. Because the expansion we observe is not happening at the edges or in a particular direction. It is happening throughout space itself. And so, when we reverse it, the entire universe contracts together. This idea can feel a little unusual at first. We're used to thinking about beginnings as events that happen in a specific place, like a spark in a dark room or a drop of water falling into a still pond. But the beginning of the universe, as we are beginning to understand it, is not like that. It is not an explosion into space. It is the unfolding of space itself. And so, as we trace this expansion backward, we are not watching things move toward a point within space, but toward a state in which space itself was different, denser, hotter, more tightly connected. To sense this more gently, you might imagine a loaf of bread rising slowly in an oven. As it expands, the raisins embedded within it move further apart. The dough stretches, carrying them along. Now imagine reversing that process. The loaf begins to shrink. The raisins move closer together. The entire structure becomes more compact. But there is no single point where everything gathers from outside. It is the entire loaf that changes, everywhere at once. In a similar way, the early universe was not a small object sitting in a larger emptiness. It was the entire universe itself, in a state that was far more compressed than it is today. As we continue to rewind this process in our imagination, the temperature begins to rise, not suddenly, but gradually, steadily. Because when space becomes smaller, energy becomes more concentrated. Light, matter, everything that exists within the universe becomes packed into a smaller volume. And with that concentration comes heat. At earlier times, the universe was warmer. Further back, it was hotter still. And as we approach the earliest moments we can meaningfully describe, the universe becomes an extremely dense, intensely hot environment, so energetic that the familiar structures we know today cannot yet exist. There are no stars, no galaxies, no atoms in the usual sense, just a dense, glowing state, filled with energy, particles and light interacting in ways that are difficult to picture, but follow from the same gentle logic we have been building. This is what we refer to, softly and somewhat imperfectly, as the beginning of the universe, often called the Big Bang. But that phrase can be a little misleading. It suggests a sudden explosion, a burst outward from a single point into empty space. In reality, the idea is quieter and in some ways more profound. It is the beginning of expansion, the moment when the universe in its earliest known state began to grow, not into something else, but as itself, expanding, cooling, evolving over time. And as this expansion continued, the universe began to change. Gradually, as it cooled, particles could combine, structures could form. Light, once trapped in a dense, opaque environment, would eventually be able to move freely. But at the earliest stages, none of that had yet happened. The universe was more like a glowing fog, dense and filled with energy, where light could not travel far without interacting with the matter around it. If you imagine standing in a thick mist where visibility is limited and everything feels close and indistinct, you can begin to sense what this early state might have been like. Not dark, but not transparent either, filled with light, but not yet allowing that light to move freely across large distances. And this is where something quietly remarkable occurs. As the universe continues to expand and cool, it eventually reaches a point where that fog begins to clear. Not all at once, but gently. Gradually, conditions change in such a way that light is no longer constantly scattered. It can begin to travel freely, moving across space without interruption. And when that happens, something profound is released. A faint glow, carrying with it a record of that early moment, a kind of afterlight, still present, still surrounding us, even now. But at this stage in the story, we're not yet observing that glow directly. We're simply approaching the conditions that made it possible. The universe, once dense and opaque, is becoming clearer, more transparent, more open, and as it does, it leaves behind subtle traces of its past, traces that we can still detect if we know how to look. This idea that the universe has a history, that it has evolved from a hotter, denser state, is not based on a single observation. It emerges naturally from the simple act of reversing what we see today, from noticing that space is expanding, and gently asking what that implies about the past. It is a quiet form of reasoning, patient, careful, following the thread of observation backward, step by step, until the picture begins to take shape. And what that picture suggests is something both simple and profound. That the universe, as vast and calm as it feels today, was once very different, smaller, hotter, more connected. A beginning, not in the sense of a sudden event in space, but as the earliest chapter in a story that continues to unfold. And as we move forward, we will begin to see how that early chapter has left behind a faint but measurable imprint, a signal, still present in the universe today. Quiet, subtle, but unmistakable, a soft echo of the universe's first light. As we follow the story of the universe backward, as we imagine it becoming smaller, hotter, and more tightly connected, we eventually arrive at a moment that is both quiet and profound, a moment when something changes, not dramatically, but gently. The dense, glowing fog that once filled the universe begins to clear. Light, which had been constantly interacting with matter scattering in all directions like a soft haze, is finally able to travel freely. And when that happens, something remarkable is released. A faint glow, not from any one star or galaxy, because none of those structures fully existed yet in the form we recognize today. This glow belongs to the universe itself. It is the light that was present at that early moment, now set free to travel across space, and even now, after billions of years, it is still here, still moving, still surrounding us. If you imagine a room filled with thick mist, where visibility is limited and everything feels close and blurred, you can begin to sense this transition. At first, light struggles to move through the fog. It is scattered, redirected, absorbed and re-emitted again and again. But as the mist slowly thins, the room becomes clearer. Light begins to travel in straight paths. Shapes become visible. Distances open up. In the early universe, something similar occurred. As space expanded and cooled, the conditions changed in such a way that particles could combine into more stable forms. The constant scattering of light gradually decreased until eventually, light could move freely across vast distances. This moment is sometimes described as the universe becoming transparent. Not suddenly, not like a switch being flipped, but gradually, softly, like a fog lifting in the early morning. And the light that was released during this transition did not disappear. It continued its journey, stretching gently as space expanded, becoming softer, longer in wavelength, but never fully fading away. Today, this ancient light still fills the universe. It is everywhere, not visible to our eyes, because it has stretched so much over time that it now lies in a much gentler form of radiation, far beyond what we can see. But with sensitive instruments it can be detected. A quiet background glow, uniform in all directions, a kind of whisper from the early universe. This glow is often called the cosmic microwave background, though you can think of it more simply as the afterglow of a time when the universe first became clear. What makes this discovery so powerful is not just that the glow exists, but what it tells us, because it carries with it a memory, a record of the universe at a time when it was very young, only a few 100,000 years into its long history. By studying this faint light, scientists have been able to learn about the conditions of that early time, the temperature, the density, the tiny variations that would later grow into galaxies and clusters. It is like looking at a photograph of the universe in its infancy, a snapshot, preserved in light. And yet, perhaps the most gentle and surprising aspect of this story is how close this ancient signal is to us. Not in distance, but in presence. Because this glow is not something far away, hidden in a distant corner of space. It is here, all around us, passing through us at every moment. There is a quiet detail, almost easy to overlook, that brings this idea closer to everyday experience. If you have ever watched an old television set tuned to no particular channel, you may have seen a soft flicker of static, a gentle pattern of light and noise across the screen. Most of that static comes from various sources, signals, electronic noise and other effects. But a very small portion of it, just a tiny fraction, is something else. It is this ancient glow, a faint echo of the early universe, still present, still detectable, even in such an ordinary setting. It is a subtle connection, a reminder that the story of the universe is not something distant or abstract. It is woven into the very fabric of the present moment, into the light that surrounds us, even when we're not aware of it. And as we take this in, slowly, gently, another realization begins to form. This glow tells us that the universe was once much hotter, much denser. It confirms the picture we began to build by reversing the expansion of space. It shows us that the early universe was not empty or static, but filled with energy, evolving over time. And from this we can begin to estimate something remarkable, the age of the universe itself. By studying how this light has stretched, how it has cooled, and how it fills the cosmos, scientists have been able to determine that the universe has been expanding for a very long time, roughly 14 billion years, a number so large that it almost resists imagination, and yet it emerges naturally from the quiet evidence carried by this faint glow. There is something deeply calming in this, that such a vast history, such an immense span of time, can be traced through something so subtle, not through grand dramatic signals, but through a soft, persistent background of light. And as we let this idea settle, another question gently returns, the one that has been with us since the beginning. Why is the night sky dark? Now, with this new understanding, the answer begins to take shape, not as a single explanation, but as a combination of ideas. The universe has a history. It has not existed forever in its current form. Light from distant regions has not had infinite time to reach us, and as space expands, that light is stretched, softened, sometimes beyond visibility. Together, these effects create the darkness we see, not as an absence, but as a reflection of the universe's evolution. And as we move forward, we will gather these ideas together. We will bring them into a single, gentle understanding, one that connects the vast scale of the cosmos with the quiet darkness of the night sky. And in doing so, we come a little closer to answering one of the oldest questions we have ever asked, not with urgency, not with finality, but with a calm sense of clarity, slowly unfolding. By now, the pieces of the story have begun to settle into place. We have followed the universe from a quiet sky of fixed stars to a vast expanse filled with galaxies. We have learned how distance can be measured, how light carries information across time, and how space itself can stretch, gently widening the gaps between everything. And along the way, one simple question has remained with us. Why is the night sky dark? It is such a familiar experience that it rarely feels like a mystery. When you step outside at night, you expect darkness. You expect the sky to be mostly empty, with stars scattered across it like small points of light. But as we have seen, if the universe were infinite, unchanging, and filled evenly with stars, then every direction you look should eventually lead to a star. The sky should glow, softly but completely, with overlapping layers of light. And yet, it does not. Instead, we see darkness. Now, with everything we have learned, we can begin to understand why, not through a single explanation, but through a gentle combination of ideas that fit together quietly and naturally. The first part of the answer lies in time. The universe has not existed forever in its current form. It has a history, a beginning, in the sense that it has been expanding and evolving for a finite amount of time, roughly 14 billion years. This means that light has not had an infinite amount of time to travel. Even though light moves incredibly fast, so fast that it can circle the Earth many times in a single second, it still takes time to cross vast distances. And because the universe has a finite age, there are regions so distant that their light has not yet reached us. If you imagine standing in a dark landscape surrounded by distant lamps that are slowly turning on one by one, you will only see those whose light has had time to reach you. The rest remain invisible, not because they do not exist, but because their light is still on its journey. In a similar way, the universe we observe is limited to what is sometimes called the observable universe, a region defined not by physical boundaries, but by the distance light has been able to travel since the beginning. Beyond that, there may be more stars, more galaxies, but their light has not yet arrived, and so they do not contribute to the brightness of the sky. The second part of the answer lies in the expansion of space. As we've seen, space itself is stretching, Distances between galaxies are growing, and as light travels across these expanding distances, it is gently stretched as well. This stretching does not just change the direction of light, it changes its nature. The light becomes softer, its energy spreads out. Over very long distances, it can be stretched so much that it moves beyond the range of visible light, becoming something far more subtle. You can think of it like a sound that becomes lower and softer as it moves away from you, until it fades into something you can no longer hear. In the same way, light from extremely distant regions of the universe can be stretched into wavelengths that our eyes cannot detect. It is still there, still travelling, but no longer visible. And so, even though there may be countless sources of light across the universe, much of that light is simply too stretched, too faint, or too distant to brighten the night sky. The third part of the answer lies in the structure of the universe itself. The universe is not filled evenly with stars in every direction. Instead, stars gather into galaxies, galaxies gather into clusters, and clusters are connected by vast filaments with enormous regions of emptiness, voids, stretching between them. This structure means that light is not distributed smoothly across the sky. There are directions where stars are more concentrated and others where space is more empty. The result is a sky that feels sparse, with darkness dominating and light appearing in scattered points. When you bring these ideas together, finite age, expanding space, and structured distribution, a clearer picture begins to form. The darkness of the night sky is not an absence of light in a simple sense. It is a reflection of the universe's history, a sign that the universe has not existed forever in its current state, a sign that space is expanding, stretching, light as it travels, a sign that we are observing only a portion of a much larger reality. And perhaps most quietly of all, it is a reminder of where we are. Because when you look up at the night sky, you are not seeing everything that exists. You're seeing a bubble of light, a region defined by time and distance, by what has had the chance to reach you. Beyond that bubble, the universe continues, calmly, silently, carrying on in ways we cannot yet observe. There is something gentle in that realization. The darkness is not empty, it is simply beyond our current view, and in that sense the night sky becomes something more than a backdrop. It becomes a kind of boundary, not a physical edge, but a limit of perception, a soft horizon shaped by time itself. And as you rest with that thought, the darkness may begin to feel different, not like a void, but like a quiet space filled with possibility, a reminder that even after all we have learned, after measuring distances, mapping galaxies, tracing the history of the universe, there is still more beyond what we can see, still more waiting, not hidden, but simply distant. And in that quiet distance, the story continues.